First, we're going to take a look at what happens when I take a couple of capacitors and I put them together in a circuit in a parallel arrangement. And so we are going to be looking at capacitors first in parallel. The symbol for a capacitor in a circuit looks something like this. We just draw two plates that are separated from one another, which have leads on opposite ends, which could be attached to something. If I take this capacitor and I attach it to a battery, so here's the battery, it has a positive terminal and a negative terminal. When I initially attach this capacitor to this battery, which might have a voltage V, the capacitor does not have any charge stored on it, but the moment I connect that to the battery, we know that current is going to begin to flow this way. We define current as the direction that a positive charge would be moving, and so of course the electrons would actually be going the opposite way. And so as this charge begins to flow, there will be negative charge that accumulates on the bottom plate of the capacitor, and there will be positive charge which accumulates on the top plate of the capacitor. And the current will continue to flow until the voltage across the capacitor is equal to the voltage across the capacitor, Vc, is equal to the voltage of the battery. And so there's a relationship between the voltage across the capacitor and the current. The current initially is strong and the charge is flowing readily, and as the voltage across the capacitor increases, as Vc increases, and the charge on those two plates of the capacitor increases, the current will start to decrease. And eventually the current will stop flowing once Vc is equal to V. We've also seen that the voltage across the capacitor, the capacitance of the capacitor, and the charge stored on the plates are related by a simple equation which says that the charge stored on the plates, Q, is equal to the capacitance of the capacitor times the voltage across the capacitor's two plates, that potential difference. So what I'd like to do now is draw a circuit where we have a couple of capacitors in parallel and see what happens. So if I have a battery, plus and minus terminals with a voltage V between those two terminals of the battery, and I draw one capacitor, which I'm going to call C1, it has a capacitance C1, and then a second capacitor, which has a capacitance C2, like this, then those two capacitors are in parallel. I know that the two capacitors are in parallel because there are multiple paths for the current to flow. The current could flow from the battery through the branch which contains C1, or the current could flow on the larger loop which bypasses C1 and flows out to the capacitor with C2. I know that each of these capacitors is going to store a certain amount of charge. The charge that will be stored by C1, so Q1, is equal to the capacitance of C1 times the voltage across it, which for now we'll call delta V1. The charge stored on capacitor C2, Q2, is equal to C2 times the potential difference across that capacitor. When we learned originally about parallel circuits, we found that any element that is connected directly to the battery like this, where the positive and negative terminals of the capacitor are attached directly to the battery, or at least in such a way that there's nothing between it and the battery, then the voltage across that circuit element is equal to the voltage of the battery. So Q1 is not just equal to C1 times delta V1, but it's also equal to C1 times the voltage of the battery, V. And the same thing applies for Q2. Q2 is equal to the capacitance C2 times the voltage of the battery, V. And so we could express the total charge, Q, as the charge stored on the first capacitor plus the charge stored on the second capacitor, which means that the total charge stored on the capacitors would be equal to C1 times V plus C2 times V, which means that we could also write this as C1 plus C2 times the voltage V. And so the total charge, Q, divided by the total voltage, or the voltage of the battery, V, is equal to C1 plus C2. And you should be able to imagine that if we just had another capacitor in parallel, then we would just have another term added on here, plus C3, plus C4, etc. And so when I have capacitors in parallel, the capacitances add up. They get bigger. Which is to say that if I put capacitors in parallel, the amount of charge, Q, that I can store per volt of the battery increases. And so lastly, for the parallel arrangement, we know that the equivalent capacitance, or the total capacitance for a parallel arrangement, Cp, is equal to the sum of all the capacitances of the individual capacitors added up. And we don't know how many there's going to be, and so we just write Ci, and we add up until we get to the ith capacitor. And so we're just going to keep adding them up all directly. Very easy to find the equivalent capacitance for parallel arrangements. Now I'd like to look at what happens when I take some capacitors and I attach them in a circuit such that they're in series, such that there's only one path for the current to flow. So if I have a battery, positive and negative terminals, which have a potential difference across them of V, and then I add in two capacitors. Here's one, and then here's the second one. There's only one path for the charge to flow around this circuit, and so those two capacitors would be in series. And so if the capacitance of the top one is C1 and the capacitance of the bottom one is C2, we need to figure out how is this different from the parallel arrangement. I know that in this case, again, the current will flow out of the positive terminal of the battery because it's defined that way, and that means that the electrons are coming out of the negative terminal of the battery, being repelled by that lower voltage terminal. And so we should find that the moment these capacitors in series are attached to this battery, there will be charge, negative charge, that starts to accumulate on the bottom plate of C2 and positive charge that starts to accumulate on the top of C1. The moment that starts to happen, you might wonder how these capacitors become charged, because charge is not flowing across these capacitors, yet both of these capacitors become charged. What happens is, due to the positive charge that accumulates on the top plate of C1, there is a repulsion of positive charge on the bottom plate of C1, which means all that positive charge is being pushed down to C2, which means that what we have left on the bottom plate of C1 is excess negative charge, and that positive charge, which is repelled by the top plate of C1, is also attracted to the bottom plate of C2. And so that's how, despite there not being any charge that's flowing across the separation of the plates of a capacitor, capacitors in series can still become charged. And by the conservation of charge, I can't have more positive charge that accumulates on the top of C1 than I have negative charge that accumulates on the bottom of C2. And the plates of the capacitors are not going to be charged differently themselves. And so for that reason, we have a charge plus Q on the top plate minus Q on the bottom plate of C1 plus Q on the top plate of C2 and minus Q on the bottom of plate C2. And so for that reason, the charge on capacitor C1 is equal to Q, and the charge on the capacitor C2 is equal to 2. And so for capacitors in series, the voltage is not the same. The voltage drop across those capacitors is not necessarily the same, but the charge on the two capacitors is the same. And so once again, we're going to use the fact that Q is equal to C delta V to find the equivalent capacitance. I know that 1 divided by the total capacitance is equal to the total voltage divided by the total charge. So I could write this as 1 over the capacitance is equal to delta V1 plus delta V2. The sum of the voltage drops across the two capacitors needs to equal the terminal voltage, V, divided by the total charge, Q. From here I know that I could write this as delta V1 divided by Q plus delta V2 divided by Q, because they have a common denominator. If I look back up at the equation that relates Q, C, and delta V, I could write this as 1 over the total capacitance is equal to 1 over C1 plus 1 over C2. And the reason for that is I know that 1 over C is equal to voltage divided by charge, and that's what we're staring at in those terms on the right-hand side. So, similar to the relationship that we found for resistors in parallel, the equivalent capacitance for capacitors in series is 1 over C1 plus 1 over C2, and I have to keep adding these for each capacitor until I've added them all up, and then I need to find the inverse of that to find the equivalent capacitance. The way that we write this is 1 over the equivalent capacitance for a series arrangement is equal to the sum of 1 over the capacitance until we've added them all up until we get to the ith capacitor. So we'll write 1 over Ci summed over I is equal to 1 over the equivalent capacitance for a series arrangement. The last thing that I'd like to point out is it would be a very good idea for you to go back and try to relearn a little bit about what we learned about using resistors in series and parallel combinations. Briefly, I will remind you that for a series circuit, we found that resistors add directly. So the resistors in a series circuit could be summed up directly. You just add up the resistance of each one to find the equivalent resistance. And then for capacitors, we have the equation which we have just shown here. 1 over CS is equal to the sum of 1 over each of the capacitances. And so it's kind of like the opposite rule that we would expect. And then for a parallel circuit, we know that we need to do 1 over the equivalent resistance for a parallel arrangement is equal to the sum of 1 over each of the individual resistances of the resistors. And then lastly, as we learned in the beginning of this video, I know that for a parallel circuit, the capacitors just add up directly. So Cp is equal to the sum of just all the capacitors until we've added them all up.